Hey, and welcome to a lesson on calculating slope slash average rate of change. So by the end of this, you should feel really comfortable with finding the average rate of change from a table, from a graph, and from a function, and then be able to apply those skills to a question involving real-life application. Okay, so those are learning targets for today. Now, let's just start with the formulas, the ones that you'll get on the reference table of the regions. So the first one is the slope, the y2 minus the y1, x2 minus x1. So that's the simple one, straightforward one. The average rate of change is the same formula, it's just in terms of function notation. So the second output minus the first output over the second input minus the first input. Okay, so just another way to say the same thing. Let's go ahead and get comfortable with using both of those formulas with the following questions. Now, some of these may have been updated from what you have in your notes. So if you see something a little different, like in this case, the interval notation 0 less x less than 2, please make sure you change that. And in addition to that, we got to put some equal signs underneath both of these, because if not, we're not going to be able to do this correctly. So let's go ahead and find the average rate of change, or the slope, for this table when the x values go from 0 to 2. Now remember that this is just simply telling you that when x is 0 and x is 2. So between those two x values. And we have those points on the table. We have one here and we have one here. Now we don't need this one and we don't need this one. We're simply trying to go from 0 to 2. With this being the x value and x value, the first one and the second one. And so this is its corresponding y value. So the first one and the second one. And so as soon as you have those two labeled, very easy to put into your slope formula as 8 minus 2 over 2 minus 0. All right? Subtraction is all that's left. 8 minus 2 is 6. 2 minus 0 is 2. And we could definitely leave it as 6 over 2. But if you want to go to simplest terms or unit rate, 3 over 1. Okay? No context for this. We don't know what we're talking about, but we'll soon add that. That will change. All right, the next one. We want to evaluate this from 2 less than x less than or equal to 4. Same idea, not complicated. It's just saying when the x value is equal to 2 and when it's equal to 4. So when given all of these choices, we got to narrow it down to just 2 points, and that was incorrect. I need to get rid of the 1, 2. I need the 2, 19, and the 4, 33. Okay? Remember that a table of values is just a list of points that come to us as x on this side, y values on this side, and because this point came first, it gets y1, x1, and this gets x2, y2. So the labeling certainly will help you when it comes time to putting it into the slope formula. So let's go ahead and do y2 minus y1. The second y value minus the first, and the x2 minus the x1, 4 minus 2, and we're on our way. 33 minus 19, how about 14? 4 minus 2 is 2. Go ahead and divide for 7. All right, in simplest form, unit rate form, 7 over 1. So that's why we want to get it down to per 1, easier to compare numbers with. Okay? Now it's time to go to that function notation. So if I was looking at this and was asked, and again I need to put a little underlining here so that this is less than or equal to, less than or equal to, I'd be asked to evaluate this function at f of 1 and f of 4. Okay, so as fun as that sounds, I know that a lot of you are kind of moaning and groaning. We have an easier way, and that easier way would simply to be using the calculator. Okay, so we're going to use the calculator, and hopefully you remember this from the beginning of the year, where we simply press the y equals key. Once we do that, we want to enter the equation exactly as we see it. So I have added a little bit to this, so it's not the same as what it was in your notes, because that linear, we could have found the slope too easily, and I'll talk about that in a little bit. But I want to enter in what was added to this, -2, then the x, and then I squared it. Okay, so I did change, again, the example so that we had a quadratic. Did anybody notice this was a quadratic? Yeah, because it had x to the second power. So that is the quadratic equation for g of x. And now I want to see that table of values. Remember, this is second and graph, and there it is. Now we want to see it from 1 to 4. And good news, my calculator is all set. Maybe you have to scroll up and down in yours, but I simply want to use this point here, not this one, not this one, and this one here. All these other numbers are just kind of noise to me. So obviously not linear, so it's not going up by the same amount every time. So the slope formula, the average rate of change formula, very important to us here. Remember, if we wanted to label this, here's the x column, here's the y column. This point came first, label it 1. This point came second, label it 2. I'm going to go from this right back to the notes and substitute it into the formula. Now, maybe a good idea for our notes to get down the table of values. So that was 1, 5, 2, 2, 3, negative 5, and 4, negative 16. But again, we needed just the 1, 5, and the 4, 16. Always the second value minus the first value. And so that would give us 4 minus 1. Once you get the hang of this, I think a lot of it just becomes memorization. Have the same sign, so remember, same sign, add them up. And 4 minus 1 would simply be 3. Fine number there, but an even better answer is negative 7, or maybe a unit rate of negative 7 over 1. All right? Not so bad when you had that calculator. Now the next one, we haven't talked a lot about solving in 1B yet, solving this year yet for y, but we're going to have to in order to put this in the calculator. So let's start with that, and let's go ahead and divide by 2. Now I did change this problem a little bit from the example, and again, if it was as is, it's going to tell you the slope just by looking at what this number is in front of x. So I did add the x squared to this problem so that we had a quadratic. So this is going to give us y equaling negative 3x to the second power plus 5. And again, we cannot tell the slope of the quadratic just by looking at it. All right, no number there just tells us the slope. So in order for us to find the slope from 2 to 5, I could substitute these in for x to get y values, or just use my calculator, which is what I'm going to recommend. So let's get rid of our old notes here and go to y equals, clear out whatever I have previously, and enter in negative 3x. I can only enter in this one because it's been solved for y. Square it, add 5. I want to go ahead and look at the table of values to find what I need. Second table, and I'm again looking for when x is 2 and 5. My table is already there. Maybe yours would take a little bit of scrolling up and down. Back to the notes. Not a bad idea to show what you're doing. We're using the graphing calculator. Best way to show that is by putting down the table. Go ahead, start at 2, and then go in order all the way to 5. That wasn't that big of a deal. Go ahead, put the y value that matched. From the calculator, it was negative 7, negative 22, negative 43, and negative 70. Now, why am I showing values that I don't need? It just kind of helps. It just kind of helps the person that's grading this see that you're pulling this from a table of values. So, next up is the formula. So let's go y values first. So y2 minus y1, negative 70 minus negative 7. Ooh, double negative there. Let's change it right now. Adding a positive. And then let's do the x2 minus the x1. And where am I coming up with this? Again, this right here told me to use this point. And then this right here told me to use the point with the 5 in it. That's all it's saying, okay? No math, just telling us where to look. Next up is 5 minus 2. It's always easiest to subtract those input values. All right, up top, I'm not going to add. The signs are different. I'm going to actually subtract. Negative 63. 5 minus 2, pretty simple, is 3. Now let's simplify this down. So 3 goes into 6 twice, 3 goes into 3 once. Negative divided by positive is in fact a negative. So negative 21 as a unit rate, negative 21 over 1. And I'll show you why that unit rate is important in just a moment. Quickly moving on to when this is just a line. Again, the average rate of change is simply the slope. So if I went ahead and looked at this and found the slope between 2 points, going down 2 and over 1, down 2 over 1. the rate of change is really the m value, or the slope, which is really the rise over the run, which is simply -2 over 1. Okay? If we knew the y-intercept, which we do here, this is -3, we can see that the equation of this is y equals, well, the slope followed by x minus 3. And the reason why I changed those examples previously is because this slope right here tells you the average rate of change. It tells you all of these things. So there's really no reason to do any of that calculator stuff if it's just a linear equation. All right, let's finish up with this one, and hopefully you're already ahead of me. You want to find 2 points. You don't always have to use the y-intercept. You can use any 2 points, as long as they make, a nice little crosshair. So it's 2 and 1 here. So I'll keep it simple. The slope, the average rate of change, is +2 over 1 because it's going up as it goes to the right. Okay? Pretty simple when it's given a line. But what if it wasn't a line? What if it was like one of those U-shaped, like the quadratic that we saw? So let's kind of plot one of these out here and draw it in. So what you're going to be asked to do is find the average rate of change between 2 points. So let's say that it was this one and this one. Okay, you would find those 2 values. So this is 1, 2, 3. This is -3, 0. And then this is 1 down, 1, 2, 3, 4. So -1, -4. And once you have these 2 points, these 2 x and y's, 1, 1, 2, 2, you'd use the same formula. Okay, so obviously that's not on your paper, but this is kind of reviewing what we did last year. So I just wanted to show you the difference between a linear and a quadratic in terms of finding the average rate of change. Any questions about that, please let me know. All right, now let's go ahead and find the average rate of change in a real-life formula. And I can tell you just by looking at this, this is a former Regents question. So you know that this is on the Regents, and that's pretty much one of the important parts of why we're learning this. So we want to find the average rate of change in millimeters per year of a person's pupil diameter from age 20 to 80. Now, if we're kind of looking at this table, we can see that the size of your pupil is decreasing, which I didn't know. So that's kind of an interesting fact. And it's decreasing every 10 years, so every decade. So we want just the 20 and the 80. And everything else in the middle is just noise to us, okay? Again, if we're thinking about this in terms of x and y, x on the left, y on the right. First point goes first in the table. Second point happens second. So since that formula is not on this page, I'm going to write it down. Now, I could have used the function one as well, but again, they're both the same, and this one tends to be a little easier to use. So I go ahead and I just put the numbers in. 2 3/10 minus 4.7. y2 minus y1. x2 minus x1 times, so 80 minus 20. And again, you're just trying to find the difference in years. The difference between 80 and 20 is 60 years, okay? Pretty straightforward stuff. The other thing is this decreased in size by 2.4 milliliters. All right, millimeters, not liters, millimeters. Now that is a rate of change, but it's not the per year. All right, so we need to divide this to get the unit rate. And so if we did that, it'd be -0.04 millimeters per year, because again, this is over 1. And that's pretty much it. Straightforward. You could have gotten this without actually doing 20 and 80. You could have gotten this from every single point, because this is all going down 4/10. It's a constant rate. What type of function operates at a constant rate? Linear, right? Now, it didn't give us the 400s, it gave us 4/10. And the reason is this is decreasing by 10. So if we put 0.4 over 10 and divide it, guess what? You get 0.04, the same average rate of change. Okay? So I'm just showing you this because of the relationship to a linear function and the average rate of change. All right, last question. We're going a little bit long here, out of time. So I just wanted to show you that if we did this, you'd have to change 3 p.m. to 15 because we'd have to base it out of military time. It wouldn't make any sense if we didn't. So I ran out of time, but there's the work. Feel free to pause the video to get anything of that down and let me know if you had any questions in class.